Hi, I'm Ken Baker with Better Bricks Education and Training. Thanks for coming tonight. Always appreciate having a good group of folks here. We have a great presentation tonight, and I'll introduce Jonathan Heller in just a minute. First, I want to thank our sponsors. Of course, the U of I Integrated Design Lab, the Bozeman Integrated Design Lab, or the big sponsors, in Northwestern Energy and Idaho Power. Northwestern's in Montana, and we have folks in Montana hopefully watching tonight. And Idaho Power, there's a lot of you in this service territory here, so we thank them. And there's other people, USGBC and such, that help us put this together every year. So this is our fall series. This is the third session. We have two more after tonight. The next session is going to be December 3rd, and it's going to be real interesting. Let me plug that for a minute, because I saw this gentleman speak from ASHRAE. He was the president of ASHRAE, Dick Byrne, and I saw him speak last year at the ASHRAE conference, and it was so good that I not only started taking notes because I was learning things, but the big thing was I was really learning things from this guy. He knows about engineering, and he makes it available to the architects too. So I think that's a good thing. So Dick will be here talking about cooling strategies for peak loads, and I think that'll be really good on December 3rd. So come around for that one too. With that, for those on the web, if you're watching and you have a question for Jonathan when he's speaking tonight, well, you can email idl@uidaho.edu. That's idl@uidaho.edu, and there's someone that's watching, and we'll get the question to Jonathan, so please do that. Jonathan Heller is here tonight. He's going to talk about case studies in grocery stores, integrated design, commissioning, and tuning. And Jonathan's been working in this field for quite some time. I was telling Kevin, I haven't seen Jonathan for years. It was probably the early 90s, 90 or 92, and I remember I was up in Coeur d'Alene working with the building officials during a residential construction demonstration program, and went out to this house. A couple guys from Ecotope, which Jonathan's who he's still with, a Seattle company. A couple of these really young guys from Ecotope were doing all of this field work out there and testing of these houses. And I do remember thinking, God, they're young but they're brilliant, And Jonathan was one of those two guys out there. So I'm really glad to kind of come full circle and have you here tonight to speak with us. And so Jonathan Heller, Ecotope, grocery. High efficiency case studies. Thanks.
Great, thanks a lot. So I wanted to have an idea of my audience tonight, just so I get some idea. We have architects, engineers, modelers, energy geeks. Who's? Yeah. Architect, Engineers. Students, engineering student? Architecture, okay. Architects and engineers and energy geeks, okay. Anybody else? Okay. Thanks for coming. We'll get started here. If I can. There we go. So what I'm going to talk about tonight, a little bit of what's wrong with current grocery store design. I apologize, but I have to do a little bit on thermodynamics and heat recovery design, just to go over some of the basics of that, and then I'll get into some case studies that I've been involved in and what it took to get to more energy efficient design. The main points that I will try to touch on this afternoon are that there is a lot of potential for energy conservation in current grocery stores, that there are some very significant barriers that exist in the way that we deliver grocery stores right now in the construction industry, and that what it takes to get beyond those barriers is very careful integrated design between the different portions, different contractors and designers. Careful commissioning, and then even after commissioning, going back and doing final tuning of how the store is actually operating. This is my disclaimer. I'm an HVAC engineer. I've only learned enough refrigeration to be dangerous. In the work that I did in grocery stores, I was assisted by a refrigeration designer, and Doug Scott, who's spent his career researching grocery store design and refrigeration. And like I said before, to get a good grocery store, you really need integration across the disciplines. So this is some data from a recent baseline study that Ecotope did of how much energy buildings use, existing commercial buildings. And you can see that grocery stores really stand out, 3 or 4 times as much energy per square foot of most other commercial buildings. And part of that's just because they're really energy intensive buildings, all the refrigeration that's in them. But part of it's also because they're not really designed very well. I picked a Russian store, so I wouldn't pick on any of our American businesses here, but it's not too far off of what you see in our grocery stores, this big cavernous space, open refrigeration cases on the floor making everybody cold, spilling all this cold air out into the store, ducts 20 feet up in the air trying to push warm air down to the floor, no skylights, a ton of light in there trying to make everything sparkle so that the cookies jump off the shelves into your carts. They're just not very energy efficient spaces in general. This varies somewhat, but the big electricity users, of course, is the refrigeration equipment. More than half, or about half of the electrical energy in a grocery store is going to run the refrigeration equipment. Another big chunk to run the lighting. And if there's natural gas, which most grocery stores have for heating, that's almost all that the natural gas is used for. And at least in the stores that I've looked at, the gas on a per BTU basis or an energy basis, the gas use and the electric use are almost the same. So that when you look at the total energy use picture, the natural gas use is huge. And this is something that often gets overlooked, I think, when talking about trying to improve energy efficiency in grocery stores. It's always the refrigeration systems that are looked at. It's always focusing in on how do we make the refrigeration systems better because they're the big electricity user. But what gets ignored is the huge amount of heat that's used by grocery stores. And so here we get into our thermodynamics. First thermodynamics lesson, first law of thermodynamics. The amount of energy that you put into a building is the same as the amount of energy that comes out of the building. So where do we put energy into a building? Huge amount of natural gas goes in to heat the space because we've got a huge amount of electricity coming in to the building to run the refrigeration system, whose whole purpose is to suck heat out of the space. So you've got all these refrigerated cases in the middle of the store, all the heat, gaining heat from the store, and we've got a big refrigeration system to suck all the heat out of those cases, keep everything cold, and throw that heat away on the roof. And at the same time, we've got a great big gas furnace that's burning to try to warm the place up again. A lot of electricity going in for lights, that also just becomes heat in the store. And this is pretty much how grocery stores function. Ways to do it better. Add skylights so that we can have less lights. Turn the lights off when the sun is up. Close the doors on the refrigerated cases. Don't have all these open cases sitting on the floor, pouring cold air out onto the floor. And instead of throwing all the heat away on the roof, take that heat and put it back into the air that is that's going into the store to heat the air back up to keep the people comfortable. So you just try to circulate as much of that heat from the refrigerated cases through the refrigeration system and back into the space. It sounds relatively simple, but to get it to function properly can be pretty challenging. This is some data that Doug Scott, again from Vacom Technologies, modeling with DOE2 grocery stores in these different climates and the effect of doing heat reclaim on the gas usage. And you can see in every climate it's a pretty significant measure. The only place where you could argue that it's not as significant is Miami because it's bloody hot down there. But grocery stores most anywhere in the country are unlike any other commercial building in that they're always in heating. And the reason they're always in heating is because there's all this refrigerated cases sitting out on the floor holding ice cream and frozen chickens and so forth. So it gets really cold and you got to heat them up. So heat reclaim can be a very big portion.
This was the condenser heat reclaim off of the refrigeration equipment?
Right. Instead of taking it up to the roof and putting it through the condenser, or before you take it up to the roof and put it through the condenser, putting it into the main air handler unit. And I'll show you some pictures about that in just a minute here. So that's the basic picture of how I'm proposing that heat reclaim be done. There's a lot of different ways that heat recovery has been done and is done in refrigeration systems, but this is the methodology that I'm proposing here tonight, and it's basically just that. After the compressors, before the hot refrigerant goes up to the roof to be thrown away in the condenser, you, through a three-way valve, whenever there's heat demand in the store, you send that hot refrigerant gas through the air handler and condense it in the main air handler that's supplying heat to the store. Like I say, there's a lot of different ways that this is done. This, I'm arguing, is the most effective way to do it. There's a lot of reasons why it's not universally done. It requires quite a bit more pretty expensive refrigerants. Refrigerants have gotten very expensive and more controlled. And you have to add quite a bit of refrigerant to take into account all of the additional coil and all the additional piping. It requires you to run the refrigeration system at higher pressures, which takes more electricity, and that's not the refrigeration designers have been focused on reducing that energy without taking into account the gas usage. Harder to control and monitor, and there's just not a lot of integration between the HVAC and refrigeration designers. So sorry again, this is where it gets a little bit deep, but it helps to go over and remember a few things. Refrigeration systems are all about boiling and condensing that refrigeration. That's how the magic of a refrigeration cycle happens. The compressor takes the cold gas, makes it a hot gas, pressurizes it, makes it very hot. That goes up to the condenser and cools off and turns back into a liquid, and that's what gives up all the heat, throws the heat away to the outside. The refrigerant then goes through an expansion valve, turns temperature drops, and it goes into the evaporator where it essentially boils back to a gas and sucks up all the heat from the refrigerated case. And the compressor is just the pump that pumps it around and the phase change is where all the heat happens. This is what usually happens when I try to explain refrigeration cycles to people, to architects primarily. Sorry, cheap shot. But there's a couple of key concepts. You don't have to fully understand refrigeration cycles or keep track of all that, but there's a few key concepts to remember that are important if it's really going to work right. So this is thermodynamics lesson number 2, the difference between latent heat and sensible heat. So when the gas comes off of the compressor, it makes it really hot, maybe 170 degrees. And it cools down in the condenser on the roof down to whatever temperature it is outside or close to that. Now, the cooling down part is what we call sensible heat. And a lot of heat reclaim systems, that's the only part of the heat that's being harvested, is the cooling the gas down from 170 degrees to 70 degrees. But that's really a small fraction of what's available. The primary mode of heat transfer in the condenser is turning that gas, that refrigerant gas, into a liquid. So if your heat reclaim system is not designed to do that, you're just not going to get that much out of it. Yes, it's still worth doing, but you're missing the vast majority of available energy that can be reclaimed and used in the store. The other thing to remember, the other thermodynamic concept to remember here is that heat will only naturally flow from a warmer body or a warmer area to a colder area. So you have to manipulate the conditions in your coil, in your air handler, to make them advantageous for heat recovery. If you put 70-degree refrigerant into a coil in your air handler, you're not going to get any heat out of it. I don't care how much heat is theoretically available in that refrigerant. It can't go from the refrigerant into the air unless it's significantly hotter than the air that's flowing over the coil. And it's not going to condense in that coil unless you can bring the temperature of that refrigerant down to the point where it starts to condense. So you need to have controls on the refrigeration equipment that can allow you to manipulate the pressure of the refrigerant to get it into the zone where it'll work. So a higher pressure refrigerant will have a higher condensing temperature, which will make it more advantageous to use in an airside heat recovery system. So you want to do this kind of heat recovery in an airside coil, you have to elevate the condensing temperature of the refrigerant up into the range of 95 degrees, 100 degrees, so that there's a big difference between the air flowing over the coil and the refrigerant, and you can carry that heat away in the air. To do that, it actually requires more compressor power because you have to compress that refrigerant to a higher pressure, and so the refrigeration system ends up using more energy. But the trade-off is that you don't have to burn all this natural gas to do it. The other important thing, so that's the raising the temperature of the refrigerant. The other important thing is to try to get as low of an air temperature as you can. The way you do that in a grocery store is you pull the air off the floor, because all this cold air is spilling out of the refrigerated cases, making everybody's legs cold. And if you can pull that very cold air off the floor and run that over the refrigerant coil, you have that much more ability to carry heat away from the refrigerant. And then the last point there on the slide is you have to have an adequate amount of air flowing over the coil to carry all that heat back into the space. People kind of following me? A few nods out there. So to do that, manipulation of the conditions in the air handler, what we do is we add that what we call a holdback valve, a heat reclaim holdback valve, and that can then be set to raise the pressure in the coil when there's a call for heat and the refrigerant's going this way. You throttle the piping down to raise the pressure in this coil and raise the condensing temperature up to somewhere around 95 degrees so that you can get the refrigerant to condense in that coil. And then whatever, after it goes through there, it goes through the rooftop condenser and drops as much heat that it can before it goes back to be heading to the refrigerated cases. So that's the primary area of energy efficiency for grocery stores that I'm advocating here, is that type of heat reclaim strategy. There's a lot of other possibilities for energy efficiency or energy improvements in grocery store design, including just more efficient compressors. There's quite a bit that can be done there. Better expansion valves, compressor control strategies that vary the head pressure and the suction pressure, mechanical subcooling, variable speed fans on the condensers. This is all in the realm of the refrigeration designers. And like I say, I know enough to be dangerous there, but there's actually quite a bit of work being done there that's being done pretty well. The point that's missing is the integration between what's being done by the refrigeration designers and what can be done by the HVAC designers. A lot of improvement can be done to the refrigerated case design. Like I say, the primary thing there, which kind of blows my mind the more I get into this stuff, is the prevalence of the use of open refrigeration cases in grocery stores. And it's all goes back to the marketing people and the idea that we will not buy beer if we have to actually open a door to get the beer out of the case. That's not true. Yeah, I don't know. As an engineering geek, I tend to believe that there's better ways to do that, and people will open the doors. But even in brand new grocery store designs, and grocery stores who at least mouth the idea that they want to do energy efficient design, there's still open cases scattered throughout the store with the quick little snacks that you can grab and the big wall of beer. And I think it's a cultural shift, it's a mind shift, and maybe it's only the store designers that we have to convince, because I think people, if they walk into a grocery store and everything's behind a closed door, you're still going to buy food, I think. But anyway, aside from that huge energy conservation measure, there's better fans, variable speed fans, better doors, better lights in the refrigeration cases. All of that, none of that has been, let's say, optimized. There's still a long ways to go in case technology, a lot of things that could be better. And anything that you do inside the refrigerated case to reduce the amount of energy that's being used by the lights is double duty, right? You use less lighting energy, and there's that much less heat energy that has to be pulled out of the case. So it's a very cost-effective. There's a lot of cost-effective things that can be done with the case design. Lighting and daylighting is something that has received some attention in grocery store design, but again, when we look to this as an energy efficiency measure, we have to remember that grocery stores are unlike any other commercial building in that they are always in heating. So in most other commercial buildings, if you use less lighting energy, it means you also get to use less cooling energy. Well, in a grocery store, if you use less lighting energy, it means you get to use more heating energy instead. You have to turn your gas furnace on more to make up for the fact that you turned the lights off. So the only time that lighting savings and daylighting really start to pay dividends in grocery stores are once you have implemented a heat recovery strategy. Because now instead of using more gas to heat the store, you're just using more of the heat recovery energy that you've already got to heat the store. So lighting and daylighting in grocery stores really goes hand in hand with a good heat recovery strategy. Although I think there's arguments about just the effect of natural lighting in stores, and maybe people buy more beer if stores are naturally daylit. I don't know. So that's my thermodynamics lesson. Now we'll talk about some actual stores that I've worked on. This case study is a Seattle area store, small regional chain in the Seattle area. And we were brought into this project under the auspices of the Better Bricks program from the Northwest Energy Efficiency Alliance. There was a store designed by a small chain that then decided that they backed out of it at the last minute, went out of business. This other chain came in and bought the shell and adopted the same design build team that had been hired, but they brought us in to try to improve the energy efficiency of the design and wanted to go for a high level of a LEED rating for the store. So we came in and made a number of recommendations of things that could be done to improve the energy efficiency of the design, including adding heat recovery, and presented that to the design build team, who then tried to incorporate that into their design. And again, the list of measures that were proposed included improvements to the refrigeration system, both the outdoor condenser and compressor system, and the indoor equipment, the casework, heat recovery, and other improvements to the HVAC controls, electric lights, and daylighting measures. And the store basically accepted almost all of the proposed improvements, and we tried to get that implemented in the design. And this was an early part of the presentation to the store, showing them what the measures that we were proposing were modeled to do. You can see that the large decrease in the natural gas usage, pretty good decrease in electric usage at the same time, about a $30,000 a year utility savings. So the barriers that we ran up against trying to get this implemented, the primary one, I believe, is the specialization that we have now in the construction industry, where the refrigeration people know refrigeration, the HVAC people know HVAC, the electricians know all about wiring a building, but nobody knows anything about what the other guy is doing, and they don't talk. And this is particularly true in a design-build situation, which is the way that a lot of buildings in the Seattle area are delivered. And what that leads to is people really focusing on their portion of the contract and optimizing their portion of the contract without taking into account how it might affect somebody else's design. There's also a pretty big level of inexperience with heat recovery in the industry. The large chains are doing it. They have their own designs and how to do it, but in the smaller chains, I guess, where they're kind of one-off stores, the contractors that are delivering those don't have a lot of experience integrating heat recovery. And always the speed that these stores have to go up just because of the economic climate of building delivery makes it difficult to have a very well integrated design. Some of the misconceptions that the design team had that made it difficult to implement some of this stuff. On the side of the HVAC engineer, there was a common conception that there was a significant cooling load. His experience was mostly with other types of commercial buildings. He calculated a big cooling load and sized and selected the HVAC equipment based on that cooling load. Kind of forgetting that there was 50 tons of air conditioning going on all the time in the middle of the store was surprising to me. But they were very worried the first year that it was in operation because they could not get the cooling. There were problems with controlling the cooling equipment and getting it to work right, and it was not working on the hottest day of the year. And the store got up to 76 degrees. Probably the most comfortable that store had been up to that point because people were always freezing in the store. So essentially no need for cooling at all. And yet the HVAC system was designed around cooling. Another big misconception on the part of the refrigeration designers and contractors was that, yeah, we could do heat recovery the way that you're telling us to, but it's just going to make the refrigeration system use more energy. Why would I want to design my refrigeration system to use more energy? If we have to crank that head pressures up, what's the point? It goes against everything that they'd been studying. And it was remarkable how long it took for me to hammer through their heads that, yes, you're right, the refrigeration system's going to use more energy, but the gas savings is huge. So it's just bridging across those two different disciplines is difficult. The importance of low return air was missed by everyone on the project, primarily thinking that it was only a comfort issue and that comfort issue wasn't that big. Not understanding the point that I was making earlier, that you have to have cool air running over the coils to be able to carry that heat back into the space. In this store, the low return that was originally designed was dropped out of the design partway through, and instead they were just pulling return air off near the ceiling. So the air near the ceiling in that store was 80, 85 degrees. So it's hard to get much heat off of your refrigeration system if you're starting with air that's already 80 or 85 degrees. So that was something that took a while to get through to people as well. And then the last thing I have up here is that a lot of work went into designing a pretty complicated lighting design and lighting control strategy, with the idea that different parts of the store, that once the light levels were high enough that the lights in that part of the store could be turned down. And when it came right down to it, the store managers or the people running the store came in and they just did not like the way it looked. They didn't like parts of the store having the lights off and other parts of the store having the lights on, or having half the lights off here while all the lights were on over here. Having the lights ever go off over certain parts of the store because they really wanted that sparkle on things. So the idea from the lighting designers about how much control they could really provide was not borne out by what the store would put up with. So the lighting savings were quite a bit less than were anticipated. So doing the commissioning on this store, a lot of issues came up. Some were more obvious than others. Some you can see when you're walking around, and others you have to dig and dig through the control system to see. This is an example. This is the refrigerant pipe coming up out of the roof, 2 1/4 inch pipe, necking down to a 3/4 inch pipe going into the side of the air handler. What happened there was that, again, the HVAC engineer didn't know anything about heat recovery. He went to his standard commercial HVAC equipment supplier, told him what he wanted. They selected a unit designed as a VAV unit for an office building, essentially. Constant temperature, variable volume air handler, when what we wanted was exactly the opposite: variable temperature, constant volume. And they sent it off for an aftermarket coil, copper coil for the heat recovery coil, and they put in a coil that would be typical for hot liquid, like hot water to run through or something, not realizing that it needed to take a gas and then condense it to a liquid in the coil. So that coil had to be changed out, which cost an awful lot of money. The HVAC unit has never operated properly. It took months and months to get it to communicate with the control system in the rest of the store. After this very large equipment supplier sold this piece of equipment, they then offered to help program it for another $15,000, which caused a lot of heartache. The holdback valve was missing to start with, again, because of not understanding exactly how this has to be done. Once it was finally installed, they never set it. They left it wide open because if they actually cranked it down, it would make their refrigeration system use more energy, and they didn't want that to happen because they'd been trained not to. A lot of redundant controls. The HVAC unit had a whole onboard control system that was never able to talk to the store control system. A whole separate lighting control system supplied by the lighting designers with separate controllable circuits on every lighting circuit so that they could be turned off and on independently. Controls on the refrigerant rack that could control the speed of the condensers, and then more controls on the condensers to control the speeds of the fan. The amount of savings that could have been achieved by careful integration of the designs was phenomenal. A lot of money wasted because of the speed that things had to happen and the fact that each of the disciplines was siloed in their own area and they just took care of their portion of the design and didn't talk to the other people. Well, it's not as if people weren't talking. People had weekly meetings, but it just didn't get communicated very well. As I mentioned before, the low return was eliminated because it was difficult to integrate into the architecture, and the person that made that decision just thought it was an architectural decision. Maybe it had some comfort impacts, but not that big a deal. Well, as it turns out, it actually matters. These kinds of things have to be integrated into the design. And a lot of problems with the way that the lights were circuited, so that they were circuited across different, across between the grocery area and the health and beauty supplies, so that lights, if you turned off that circuit, half the lights in each of those sections would go off instead of being circuited so that based on the way that the store was laid out. So these are all things that come up in commissioning that are really critical to making the store actually function. So we went through a commissioning process and got the store more or less functioning the way that the designers intended. And that's really what commissioning is supposed to do. It's to make sure that the building is set up based on the way that the design had intended it. But once you go through that still doesn't necessarily mean that the building is functioning the best that it could be. So we came back and did another run through it in what we call building tuning, which I think is an important step for any commercial building, because the engineers are sizing systems and setting them up typically for worst case conditions. You have to size the system to handle the worst case condition. Just that's the nature of engineering. But most of the time, buildings are not functioning that way. So somebody operating the building and keeping track of the energy use of the building really has to come back in and reset things to really operate the way that the building is actually being used. So, for example, the engineer designed the minimum outside air setting at 30% outside air based on this idea, counting up all the exhaust fans in the deli area and the occupancy and so forth, and trying to maintain a positively pressurized building. Well, it's impossible to positively pressurize almost any grocery store because the bay doors are always open. It's this big cavernous space with doors opening and closing all the time. There's really no reason to have that much outside air brought in through the air handler. So we reduced it to 10%, and there was no noticeable comfort impact. The schedules and set points were such that, again, this is something that can be pretty tricky. The heating set point was set back at night, which is a good idea, not to use so much heat at nighttime when the customers aren't there. But the set point for the heat recovery was also set back, so that in the morning time, when they wanted to heat the store back up to operating temperatures, the gas heat would come on every time because the store just couldn't heat up fast enough on the heat recovery alone. So we went back and we just said, well, there's no reason to set back the heating set point if you're using heat recovery, because you want all that energy in the store. So just leave the heating set point for the heat recovery high all the time. In fact, set it as high as you want. Set it to 72 degrees. Try to get the store up to that. Most of the time you can't get that much heat out of the refrigeration system to get the store that hot. And then you can manipulate the set point on the gas at night. We added a low return, which made a huge difference that I'll show you in a minute. we discovered that in commissioning we found that the holdback valve had not been installed. Well, so we got it installed, but the guy had come back and opened it up all the way so that his refrigeration system could float down to lower condensing temperatures. And we didn't figure that out until we had a few months of data from how much gas was being used, and we were wondering, why are we using so much gas still? For this reason. So the results of this building tuning and commissioning and measuring energy use for approximately a year, we found that the lighting energy use was still much higher than we had modeled. And again, it's primarily because the store managers didn't like the way it looked. They didn't like lights going on and off. They didn't like half the lights being on in the store and half being off. They thought that their sales would drop off if the eggplants didn't glow at people. So that's something that's important to, I think, for lighting designers to pay attention to and talk to the store managers, to not go overboard on what we think we can accomplish with that. For example, in this design, there were 4 separate daylight sensors placed throughout the store so that the amount of daylighting in the different parts of the store could be monitored. When it came right down to it, the sun was either up or it wasn't. When the sun was up, they were able to turn half the lights off in most of the areas of the store. And when the sun went down, they'd all come back on. And that was the full level of daylighting control that was really possible in the end.
Excuse me, do you know what kind of control system it was? Was it a step dimming or was it just on?
No, it was just on off, but each fixture had 2 lamps, so they were able to either have 2 lamps on, 1 lamp on, or no lamps on. But each circuit was independently controllable. The refrigeration electricity was very nearly what we modeled early on, which was somewhat gratifying. Meant that our model wasn't too far off. The gas heating energy was very high initially, reduced quite a bit after commissioning, and then reduced again quite a bit after the building tuning. And after the tuning, it was pretty close to what we'd modeled. This is the natural gas energy usage. Initial model, this is in therms per year, 30,000. When the building was first opened up, it was using more than the initial model by quite a bit. And oh, I'm sorry, when I say the initial design there, that was the design of the store before our client took over and before we proposed this whole range of energy efficiency measures. So what we predicted would be used is about 9,000. It was, right out of the box, it was using 34,000 therms a year. After the commissioning, which we found that the holdback valve wasn't installed and adjusted, that dropped it to 16,000. And then after adding the low return, it was down to 7,000. I put a note at the bottom of the slide there that if you really want to dig into the numbers of the natural gas and the refrigeration equipment and the lighting and so forth, those are all detailed out in a paper that I wrote for ACEEE, and it's in the 2008 summer proceedings. Or you can send me an email and I'll send it to you. After all of this, the next thing that was done was Puget Sound Energy helped fund the installation of these roller shades, which they're now pulling down at the end of the day. So during the night, they've at least got this much coverage on the open cases. I don't have the numbers yet for what the impact of that, but I'm guessing that it's pretty significant. So it'll be an even lower gas usage following this. The same store owner built another store recently in the area using almost the same design team. We were only involved after the fact to assist with commissioning, so we didn't get to have much of an impact on the design. New issues came up that I wouldn't have thought about before, so it's pretty challenging to get this stuff right. The design for this store went to, instead of one big centralized refrigeration rack, they used four smaller refrigeration modules that they call protocol modules, kind of distributed around in the store. And one of those went to refrigeration heat recovery to the hot water, which is a good idea, because there is quite a bit of hot water being used in these stores since they've got delis now. But remember that to do domestic hot water from this refrigeration equipment, you're really only going to get that superheat portion of the refrigeration. You can't condense, since you're trying to heat the water up to 120 degrees, you're not going to condense that refrigerant with 120 degree water. So you're only getting a portion of what's there. The other 3 units they brought up with 3 independent coils. This is looking inside the main air handling unit on the roof. Notice that there's 3 coils in parallel, and then up at the top there's a big bypass section. So 25% of the air is bypassing the coils at all times. I could never get a good answer from the designers why they did this. There's just, it almost guarantees that the natural gas will have to come on because the air won't be warm enough. Having them all in parallel means that if only one of the systems is running at much capacity at a time, then most of the air going through the air handler is not even flowing over a hot coil. But there's only so much you can do after it's designed and installed, so they're going to get what they get out of this system. And again, I don't have the data yet on it, but we are doing some measurement and verification on this store as well. Another example of why the careful commissioning and tuning is important. The set points for the heat recovery and the gas heat initially were the same set point. So we're just trying to keep the store at 72 degrees. First stage heating is the heat recovery. Second stage is natural gas. Well, there'd be a call for heat from the thermostat. It would let the refrigerant go to the heat recovery coil. 2 minutes later, the thermostat's not satisfied, so the natural gas comes on. Heats the store up to 72 degrees. There's no more call for heat, and so the gas turns off and the heat recovery turns off until the store drops down again. So it's just those types of control issues are maybe kind of, I mean, they're logical, they make sense, they're maybe kind of obvious once you get into it, but unless somebody's really paying attention to these things, it just gets missed. There's a heating set point, the store's warm. Yeah, we're using a lot of natural gas, but maybe we have to be using a lot of natural gas. It's difficult to sort these things out unless there's somebody that's really paying attention. So conclusions from all of this is that the current construction industry that's delivering grocery stores to us, well, if anybody was building new grocery stores these days, this maybe was more relevant before the economy crashed. But anyway, once we start building grocery stores again, the construction industry that we've got is not very well positioned to deliver this type of heat recovery system. Maybe in the big chains, because they have their own teams and they can they can put them all in a room and say, don't come out of there until you've got a design that everybody agrees on. But if you're going out and putting out a bid for a grocery store and getting a refrigeration designer and an HVAC designer and an electrician and so forth, that's not a great recipe for getting this type of design. It's just very difficult to do. Unless there's somebody else that's overseeing that portion of the design as maybe an owner's rep or from the utility or something, or from Better Bricks or whoever. There are a lot of savings, though, out there. Grocery stores are huge energy hogs, and they can be done better. So it's probably worth trying to figure out, even though it's difficult. And the last point there is that commissioning to the design intent is perhaps not enough, or is not enough. That there really has to be this additional step in complex buildings that could be called building tuning. That's what I'm calling it now. It could be called recommissioning. It could be called measurement and verification. But somebody has to go back a year later and really look at the energy bills and what's going on in that store if we expect buildings to continue to function well, or even to function well to start with. Then I just wanted to acknowledge the other people involved in this. Again, Doug Scott from Vacom Technologies taught me what little I know about refrigeration systems. Better Bricks funded our initial work with that grocery store. Dave Balon from my office. And I don't mean to be picking on the design team for these projects. They were inexperienced with heat recovery, but they did hang in there, and in the end, these stores do function really well. They did a good job. It's a difficult thing to do, so I want to acknowledge the good work that they did. I didn't bring any cards tonight, so if you want my contact information, you have to write it down. And thanks very much for coming to listen, and I hope that you have some questions.
Good. So, thank you, Jonathan. Starting with. And, let's ask him some questions.
Have you ever looked at taking the heat recovery, not instead of like a central air handler, having it dispersed throughout so you don't have these long runs of refrigerant?
You probably end up with more refrigerant doing it that way because you've got that much more lineal feet of piping. I have not tried that. I haven't really thought through that design, but my first thought is that it adds complexity to the whole thing, and that if you can do it with one primary central air handler that's relatively, locate it close to your refrigeration rack if you can, to keep that distance down, that probably works better. But for example, with this idea of going to the protocol units where they're scattered throughout the store, it could work with that, where you dedicate an air handler to this unit and it's just right above it. For example, that might work well instead of what we saw at the second store where they had 3 parallel coils associated with those 3 different refrigeration units. So that could be a good pairing.
On the measurement and verification side, when you were, what were the end use measures that you were measuring? What were the specific?
Well, we had circuit transducers on the lighting circuits. So we had the lighting energy directly. We had circuit transducers on the refrigeration racks and case circuits and compressors, so that we could we had the refrigeration electrical energy directly. We had gas submeter on the kitchen, the deli, because these stores have quite a high cooking load. So we were able to pull that out of the overall gas bill. Unfortunately, we did not have the overall gas use on a hourly or daily basis. All we had was the bill from the gas company. So we weren't able to zero in on that usage. It would have been better if we had that. We had a water meter just on the feed into the domestic hot water tank, and we just assumed a constant temperature in the domestic hot water tank, which is not. No, we had temperature. I'm sorry. We assumed a constant delivery temperature, but we had temperature in the tank, so we could see when it was calling for heat. So we had a pretty good picture. Some of it, you'll notice on that slide I had of the gas usage, I was a little bit maybe mealy-mouthed about modeled or inferred or measured and calculated. Those all mean something. Trying to be specific for the paper that I wrote for ACEEE, but there's various ways that I extended the measurements that we had to the whole year.
What kind of payback in number of years?
Good question. It was a little bit difficult to track. In the first go-round, it was pretty challenging because there was a store that was almost fully designed by the time that the second owner bought it. And then they brought us in and we came in and said, okay, great, we're going to change your designs. You know, you have to do this, this, and this. And it got mixed up with the things that they were told that they had to do for LEED. And so they called it all, they gave incremental costs, but it was all associated with what they just called LEED. So it was difficult to extract what was really for the energy efficiency measures and what was for LEED, and maybe how much was justifiable or not. But I'll say that our initial proposal to the store that it was going to be a 3 to 5 year payback, there's no way. It ended up costing them a lot more. And a lot of that I alluded to with all of the duplicated controls and the things that were done that based on inexperience. I don't know what the numbers were for the second store, but the numbers couldn't have been too terrible because they did it again. They did a lot of the measures over again. So I guess I would still argue that if it was done carefully, it could easily be under 5 years. And the refrigeration heat recovery alone, just on its own, it should be able to be done for a 3-year payback. There's a lot of gas, and as gas prices go up, it should be very attractive. The problem is the knowledge base and getting the contractors to design it and install it and set it up properly is difficult.
I had a question on the condensing heat recovery, do you run into any issues with just the physical size of that coil being as it needed to remove as much heat as, you know, those big banks of air-cooled condensers?
There's probably still some condensing that's going on most of the time in the condensers. But remember, it's just running in series. So however much condensing you can get out of it in the air handler, then you get that heat. And whatever hasn't condensed in the air handler, it still is going to run through the rooftop condensers. I don't actually know in this store what typically is going on in terms of how much of the condensing is done, but most of it, if not all of it, for parts of the year, is happening in there because just based on the resulting gas bills being as low as they are, there's not that much gas that's still being used.
Question in the back first, and then.
Yeah, I was just going to ask, looking at your diagram from before up with the whole back down, your diagram shows the condenser being below the air handler. Typical stores that I've been working on, the air handler is actually contained within the building at the same level as the compressor rack, as opposed to being on the roof.
Mm-hmm.
Do you have any problems, or is it still possible to allow that kind of condensing, and when the compressors do the work to push the remainder up to the condenser on the roof, as opposed to keeping everything up on the roof and keeping it connected and utilizing gravity as much as possible?
Yeah, I don't think that matters that much. I think, yeah, the condenser probably should have been shown above because you're right. A lot of times the air handler is in the building. I don't know that the location really makes that much difference. It can the stores that I worked on here, they both had rooftop-mounted air handlers and rooftop-mounted condenser units, with the compressors located in mezzanines just below the roof.
I guess my other question would be, as far as you raise the pressure to go through the reclaim coil. Then when it comes back through the holdback valve, is it flashing back to a gas to go up, or partially because it's not dropping pressure?
Partially it probably does, yeah.
So that way you're getting it, allowing the compressors to push it up.
Yeah. Yeah. And this just shows my ignorance of refrigeration systems, but that has not been a problem as far as getting logged in the condensers. But you're right. Depending on the outdoor temperature, the condensers could be operating at a much lower temperature than the air handler in the wintertime, for example. So it could be at a significantly lower pressure.
I have a much less technical question than that. I was just wondering what other building types are viable candidates for heat recovery, or does it have to happen at this scale for it to be truly effective in terms of energy savings?
Well, certainly any building that's got any significant refrigeration equipment, there's usually a use for the heat. We've certainly used heat reclaim to hot water in restaurants quite a bit, from a walk-in cooler or a walk-in freezer in a restaurant or a dining hall. Any place that has not a packaged refrigeration unit, but a separate refrigeration unit that's cooling a walk-in, for example, then there's the opportunity to take that refrigerant when it's hot, before you take it through your condenser, and reclaim heat from it. So running it around a preheat for the domestic hot water is often quite cost effective. And again, where you're going to see that is a restaurant or a dining hall or something like that. Where else? Other ways to do that that I have seen is to have the compressor or the condensers being in kind of an indoor-outdoor space or a plenum space where you could pull the outdoor air for the building through that space to just preheat it directly with the waste heat that's thrown off of the condensers. So it's kind of a more brute force heat recovery approach.
Got a question from the web here. And
Somebody's out there.
Oh yeah, there was 6 people watching you for sure. Maybe that was 600. But one of them had a question: what corrective actions via the issues in commissioning with coil design, the controllers and programming versus BAS controls, the lighting controls versus BAS controls, etc., were taken by the design builder? So what were the corrective actions that were taken by the design builder on all these systems?
During the commissioning process, I guess?
Yes.
Well, the coil design in the first case, it was fairly clear that they'd done it wrong. There was enough direction in the contract documents that the designer or the contractor was required to pull that thing out and replace it. I think the store owner shared some of that cost. The controls, I'm not sure I fully understood the question. Corrective action.
Were there corrective actions with during commissioning with coil design or the controllers and programming versus BAS controls, lighting controls?
There was a central building control system that was able to control basic HVAC functions, but primarily it's a refrigeration control system. And in most grocery stores, that is what the building automation system is really a refrigeration control system. Oftentimes it's barely controlling the HVAC and barely controlling the lighting, in that it turns things on turns certain banks of lights on at certain times. But in this case, the controls contractor was the refrigeration contractor, and I think that that's not uncommon in this type of building. So, and they were also hired to be the maintenance, to continue to operate the building, and to be on call when there were alarms from the refrigeration system. So they were pretty involved in the commissioning process and in all of the corrective action that was taken to try to dial it in. But again, we had to really hit them over the head with in fact, show them the actual gas bills and electric bills to kind of prove to them that it was worth it to do what we were talking about. Even though the client had directed them to essentially listen to us, they basically didn't believe it until we had a sit-down meeting in the client's office with their O&M person and me with the bills before we could get them to really set it up the way that we wanted them to set it up. It was very interesting. Yeah.
When you have more heat generated basically through the refrigeration system,
and you're pumping more electrical power through it, you're making that equipment work harder. Are you concerned about a life cycle cost on that equipment by making it work harder?
No, and I had that same question, and the refrigeration contractor said, well, no, actually it likes to operate it a little bit more at higher temperatures, or at higher pressures and higher condensing temperatures. So it's actually a little bit more advantageous for the equipment itself. It just uses more energy.
More efficient.
It's
Its own nature that way.
Yeah, and I don't, again, it's not my total expertise, so I don't know why, but that was one of the things that I brought up when we had this sit-down meeting. I asked that question. I said, you know, is there some other reason why you're not doing this? I mean, is this going to put your equipment at risk of breaking down? And he said, well, no, actually it likes to operate there a little bit better. I just thought I shouldn't do it because it's going to use more energy.
Were you able to find that difference, you know, the increase in electrical energy versus the drop in gas?
Yeah, and it was, in terms of dollars to the client, it was about 10 to 1. So a 10% increase in bills because of the operating the refrigeration equipment at a higher pressure, and a 10 times that much dollar savings in the natural gas.
Can you speak to the energy modeling process a little bit? You mentioned you're using DO2. Were you able to model everything explicitly?
Yeah, and that there's a refrigeration module for DOE2. I don't know, are you familiar with that? It's called DOE 2.2R or something like that. And that was done by Vacom in California. So I don't know that much about it, but there is an explicit refrigeration module that you can input details about the refrigeration equipment and head pressures and subcooling and all that good stuff. But nobody's really going to be able to use that except a refrigeration designer, somebody that really knows that stuff. So it's a very specialized area that needs more people that understand it and that can do it. It is important, and I would, if you have interest in that area, it would be interesting to get into that more, take a refrigeration class and learn how to do that. Mm-hmm.
Question. I mean, just as far as heat recovery design, the information out there as far as how to implement it and utilize heat recovery off of the systems is pretty scarce. And I was just wondering if you had any place where a person could go to find that, or where it was compiled, or if you know of anybody who's putting that together.
Oh boy, there is not a lot out there, and there's not universal agreement, we'll say, in what the best way to do this is. A lot of the chains have implemented some level of heat reclaim in their standardized designs, but mostly it's desuperheating, and they're not trying to condense in the coils. So it's simpler. There's less integration that has to take place, less control changes that have to take place, less refrigerant that has to be, less of an increase in refrigerant charge. And they're getting something out of it. It's worthwhile. But there's a lot more there that's available, that if you go to this type of design where you're condensing in the coil, it happens. And I don't know that there's really a lot of good resources out there. There's, every year there's a few more articles in the ASHRAE Journal and people publishing things there on refrigeration techniques and improvements in refrigeration design and heat recovery. But there's not always agreement there as well. So it's It's a poorly understood art, we'll say.
To it as a black art.
Yes. Yeah.
Okay, thanks.
Any other questions for Jonathan? Well, thank you again for coming. We really appreciate your
Yeah.
presentation here
Thanks for
tonight.
listening.
Sign in if you haven't. There are a few cookies left over there. If you don't eat them, the lab folks eat them.